we're going to look at inverse functions. Okay, so first of all, what is an inverse function? Well, let's say that we've got some function. We don't really care what it is. It could have any kind of shape. It could look like that. It could look like, oh, not like that. It could look like that. The key is that I want a one-to-one mapping. First of all, I want the original mapping to be a function. For every input, I must know the output. Similarly, I want to make sure that if I know the output, I can go back to a unique input. I want the inverse, the function which undoes this function, to also be a function. One-to-one. One input, exactly one output. One output, exactly one input. Okay, so let's imagine that our graph looks something like that. What I'm going to do is, if I want to do the inverse function, it's like I know the output and want to know the input, so I effectively swap my axes around. Okay, what was my y-axis becomes my x-axis. You can think of x's as inputs, y's as inputs. So what I'm going to do is I'm going to reflect in the line y equals x. If you can imagine, that would reflect the y-axis down here and the x-axis up to there. Similarly, this graph would also be reflected. So the red graph is going to be the inverse function. So our inverse function will look something like that. Remember, the inverse basically swaps your inputs and outputs. However, it would look really awkward if we actually labelled this as y and x. So just like we usually plot y equals some function of x, it would be convenient if we also plotted y equals the inverse function of x. So we get that idea that we can reflect in the line y equals x to see what the graph would look like. However, we're not actually going to change the names of these axes. We're going to relabel them, so we just have the standard convention, the horizontal will be an x, and then we can define the inverse function also in terms of x. So let's have a look at a few standard functions and see their inverses. First of all, look at some graphs that you should probably know. So we'll start off with y equals e to the x, or any number to the power of x, any exponential. So we know it has a y-intercept of 1, goes off to infinity in both directions, and has an asymptote at x equals 0, at y equals 0, sorry. Okay, so the inverse of that, I'll just reflect in the line y equals x. And again, this will be the inverse function. This is what the inverse function will look like. So if that is y equals f of x, our inverse function will look like this. And we should recognise that as the log graph. Ln of x is the inverse function of e of x, and the graph of ln x is a reflection in the line y equals x. Okay, we'll just have a look at one more. Let's consider y equals sine x. We're going to work in radians here, and we'll want to consider what's the inverse function going to look like. First of all, let's just sketch sine x. Something like this. And we'll just get some labels in pi, 2 pi, 1, minus 1, 3 pi, minus pi. Okay, cool. So you might think, oh, that's fine. We can just reflect this in the line y equals x, and we can get our inverse. Something like that. However, this poses a problem. We said that we wanted the inverse function. Although sine x is a function, for any given input. I know the output. There were many inputs that could give me that output. When we switch it round, we now notice that inverse sine of x, as we've been solving it before, is not a function. There are many values that come out of inverse sine x. So we haven't got ourselves an inverse function. What we can do though is we can restrict down the domain of sine x to between just, if we look for where we'd get unique values, we want to include all the values. If we stopped our graph there, we would get rid of all of this repetition. Okay, I don't want to have two possible values, so I just stop my graph at pi over 2. I'm going to allow pi over 2 because I do want 1. I want to be able to invert every single value. Similarly, I want to be able to get all the negative values, but then I don't need to go beyond negative minus pi over 2. After that, I just get more duplication. So let's just clear this up so that we can see it a bit clearer. I've restricted sine x to just these values. The reason for that is now when I do the inverse function, both the original function and its inverse will be inverse functions. And my graph should look something like this. Okay? And what we have there is not inverse sine written like that, because remember, when we're solving trig, we can get many values from this. If you were solving for where it equals a half, so you might have had pi over 6, 5 pi over 6, and so on. We just want one value because we want it to be an inverse function. This is what we define as arc sine x. And that's the inverse function of sine x rather than just the inverse. Okay? I'll leave you to try and think what the inverse of arc cos would look like, and y equals arc tan x would look like. Consider those, but remember, arc cos and arc tan are inverse functions, not merely the inverse. They must be one-to-one mappings. Think how you can restrict down your domain to still get all the possible values. Because we can put in, we should be able to get out any number between 1 and minus 1. So in the inverse, we should be able to put in any number between minus 1 and 1. And the inverse should spit out any number up to pi over 2 and minus pi over 2. How would you need to adapt that for arc cos and arc tan? Have a think.